said, today I'm honored to deliver my lecture on the behavior and temporal-based effects of sustainable self-consolidating concrete in bridge structures. And I would also like to thank my co-presenter, Hayder, who is one of my recent PhD graduates. This research deals with the behavior and time-dependent based effects of a sustainable self-consolidating concrete, which is targeted for bridge structures. The research consists of two major parts. Part A, which is a laboratory study of developing and investigating the overall performance of high-volume fly ash SCC. And if we have time, I'll discuss a little bit about Part B of the research, which is a field study of time-dependent behavior of high-strength SCC in Missouri Bridge A7957. I'll start with Part A, and I want to introduce the following contents of the presentation. Talk about an introduction on the topic for those that are less familiar with sustainable concrete materials development and applications. Then I'll talk about the objectives of the research, the development of this unique concrete mix design, then talk about the structural behavior in terms of shear and bond performance of this type of sustainable concrete, and wrap up with some general conclusions. There's a large demand for the use of concrete to construct infrastructure buildings, roads, bridges, and dams, and this has increased tremendously. Cement production is growing by 2.5% annually and is expected to reach 3.7 to 4.4 billion tons by 2050. However, cement production is also a key source of CO2 emission due to the extreme heat required to produce it. And as you can see here, each ton of cement requires 4.7 BTUs of energy and generates nearly 1 ton of CO2 emissions. And this is actually between 5 to 7% of global CO2 emissions. Approximately 1.5 tons of raw materials are required to produce 1 ton of Portland cement. And in the graph in the bottom right, you can see some of the metric tons per year, specifically in the United States. This industrial product, which would otherwise end up in landfills generally in the United States and cause environmental issues, can be replaced part of the cement. And in the United States, there is 50 million tons of fly ash produced each year, but just 23 million tons is used in different categories, and the rest, which is around 27 million tons, is disposed of. Now let me talk a little bit about cement. The current ACI, which stands for the American Concrete Institute, recommendation for fly ash substitution in concrete is 15 to 35%. So currently our standards allow a very modest amount of replacement of using fly ash in concrete elements. Using the excess fly ash for concrete benefits the environment and possibly concrete integrity. So high volume fly ash self-consolidating concrete, or HVEA-SCC, is proposed here as a sustainable concrete that merges attributes between high volume fly ash concrete properties and self-consolidating concrete. And as I mentioned in the previous slide, currently ACI limits to 35%. So our question is, can we start to greatly increase the amount of fly ash, 50, 60, and even 70%, thereby reducing the impact of CO2 emissions in terms of the use of Portland cement? As you can see here, there's a few concerns, I guess you could say, with high fly ash usage. This includes slower strength gain of the concrete, delayed setting time, flash set, and potentially the durability at early ages. But if these drawbacks can be mitigated, concrete with high volume fly ash will be the most straightforward way to minimize the amount of Portland cement. High volume fly ash self-consolidating concrete is a new class of concrete which satisfies design requirements, which means both mechanical and rheological, or the flow aspect of the concrete, and also addresses any environmental concerns. High volume fly ash SCC can be produced by combining the high volume fly ash up to 70% and self-consolidating rheological properties. And so this is a new type of SCC developed within this research program, as I'll talk more about. The modifications required in the mix design to produce a flowable, non-segregating SCC raises concerns on the approach used to develop the particular mix design. There's a reduction in the coarse aggregate size and also amount, and the proportions combined with an increase in paste content can lead to increased creep and shrinkage of the concrete, decreased bond strength, and an interface shear transfer contribution to the concrete shear strength. This leads to additional concerns when incorporating high contents of fly ash. And these are part of the reasons why ACI had never allowed high usage of high volume fly ash in the past. As you can see here, the main objectives of the study were to develop and validate the performance of this new targeted concrete for highway bridge structures. In order to be successful, we have to work to develop a mix that has no evidence of segregation or settlement, that has a minimum 3-day compressive strength of 2,500 PSI, 28-day strength of 6,000. This would make it usable in most applications, including some precast reinforced concrete applications, and also a minimum durability factor of 75% based on the freeze-thaw tests. And below you can see some of the various fresh and hardened concrete tests I'll talk about. This flow chart summarizes the research program of developing and investigating the performance of high volume fly ash SCC. The first step was developing the mix design. The development went through 2 phases: optimizing the binder composition, followed by optimizing the aggregate skeleton, and then coming up with a final mix. Once the mix has been developed, the mix needed to be validated in terms of its rheological properties, the mechanical properties, the durability, and then finally the structural performance, including the bond strength. Under each of these, you can see the key tests or evaluation criteria that was used to assess the performance in the various categories. Based on literature and practical considerations to design mixtures with SCC rheology, the following constraints were imposed. As seen in this figure, SCC needs to have a paste volume more than conventional concrete mixes to enhance the concrete flowability. The target rheology properties were selected based on the intended application of SCC recommended by NCHRP Report 628, which is presented in this table. So here you can see the target values for design, for quality control, and the various tests that are used to evaluate it, as well as the targeted water cement ratio, the CM content, and the maximum aggregate size. As I just mentioned, the mix design went through 2 phases. The first phase was to optimize the binder composition, and through this phase, the cementitious materials were combined and were generated using design expert software. So 3 different materials were utilized: Portland cement, type 1 and 2, type C fly ash, and type S hydrated lime. And within the use of the software program, a series of trial mixes were developed with ranges in the cement usage, the fly ash range, as well as the hydrated lime. Phase 2 included optimizing the particle size distribution of the aggregate skeleton. Fine to coarse aggregate ratios were investigated to optimize the particle size distributed of the aggregates. So in other words, if we can minimize the void space and densely pack the concrete based on the particle size, we can minimize the use of water and thereby help reduce the amount of shrinkage and creep in the mix design and optimize it. In order to do this, we need to know the gradation of all the materials used, in particular, the aggregate sources, including both the fine aggregate as well as the coarse aggregate. And in this figure over here, you can see that in terms of optimization for packing density, a sand to crushed stone ratio of 45 to 55%, sand to crushed stone optimized the packing density for the materials used. The final mixes for the design of the high volume fly ash SCC are presented in this table. And as can be seen, the sand and coarse aggregate weights were adjusted to take into account the effects of the specific gravity of the cementitious materials. The control is the standard conventional self-consolidating concrete. And then we had a 50% high fly ash content, 60% fly ash content, as well as 70% fly ash content. A local ready mix concrete producer was used to help us produce the concrete. While making the mixtures, the dry materials, including the cement, fly ash, sand, and crushed stone, and 3/4 of the mix design were added and mixed first at the ready mix plant and then brought to our structural engineering high bay lab. The following tests were evaluated to assess the fresh concrete properties of the concrete and compared to the target values to meet the rheological properties of the mix design. And you can see in this table how they compare. Also notice that the unit weight, as we add more fly ash, due to the lower specific gravity of the fly ash relative to the Portland cement, reduces the weight or the unit weight of the mix design. In addition to the rheological properties, mechanical properties were also measured following mostly ASTM procedures when applicable. We measured compressive strength, as you can see in the upper left-hand corner, with our 3-day targeted strength requirement, all satisfied that, as well as our 28-day strength requirement. And all of our mixes easily satisfied those target strength requirements. In addition, you can see the drying shrinkage behavior. Worthy of note is that the high volume fly ash SCC had the least amount of shrinkage, which is a good thing. And then you can see the results in terms of the tensile properties as well as the fracture energy. And you can see the test for the fracture energy shown in the bottom right, as well as the modulus of elasticity or stiffness of the concretes for these various mix designs. In addition, to look at the durability performance, the freeze and thaw resistance test was evaluated. And for all of these mixes, they provided very excellent durability behavior. With an air entrainment admixture, the targeted durability factor of 75 was well exceeded. Without air entrainment, it may be noted that the high volume fly ash with 70% also had outstanding performance in the freeze-thaw testing. In addition, the Rheological CPC-18 accelerated carbonation test was undertaken. This helps to ascertain the carbonation depth of the mix design. And here you can see the results of these. The fly ash ones had higher carbonation depths, That can be associated with the fact that we used hydrated lime to help the early age strength gain of the mix designs. The surface electric resistivity test was also undertaken to provide a rapid indication of the concrete's resistance to the penetration of chlorides ions. And in this figure, you can see that the mixes with 0 and 70% replacement exhibited very low ion permeability based on this criteria here, which is excellent. And even the 50 and 60% provided very, very low, and these two negligible. Now I will go into the shear behavior aspects of the mix design. In general, shear failure is frequently sudden and brittle, and this figure gives you an idea of how the scatter of the data is. In addition to modifications required in the high volume fly ash SCC mix, designed to produce a flowable, non-segregating, self-consolidating concrete, might raise concerns by engineers and designers regarding the high volume fly ash shear strength. So one of the concerns about shear strength and self-consolidating concrete is the behavior of aggregate interlock. Aggregate interlock allows additional shear capacity from the concrete based on the size and volume of coarse aggregate. Of course, in SCC, we use smaller aggregate and fewer coarse aggregate in the mix, raising the concerns about that along with dowel action. These are two of the critical 4 compositions that contribute to shear strength in concrete. In order to evaluate this, a test matrix was developed with the following parameters of the beam cross-section, the shear span to depth ratio of 3.25, and then the tensile strength of the longitudinal reinforcement and the shear stirrups when used. Here you can see the test setup in our structural engineering laboratory. In terms of the test matrix, you can see that the 3 different key aspects of high volume fly ash were investigated. It may be noted that we didn't do the conventional concrete in this particular test study because we had done it previously. And here you can also see the different types of members indicated here with the beam ID. Some of these included shear reinforcement, and some included top reinforcement, bottom reinforcement, depending on the lap splice, as you can see indicated here. The main variables investigated included the replacement level, the longitudinal reinforcement ratio, as well as shear reinforcements with and without stirrups. And here you can see the development of these test cages, the reinforcement for these test specimens in the laboratory, as well as fabrication of these. Again, here you can see the fabrication and the placement of the high volume SCC, and then the test setup immediately prior to testing. Following the test results, the test data was summarized in this table for the 50% fly ash, 60%, and 70% fly ash. As you can see here, all of the tested beams failed in shear. In general, there was no major difference in the cracking and ultimate shear forces for the same reinforcement details, with the increase of cement replacement levels. Beams with shear reinforcement exhibited high shear resistance, and the shear reinforcement contributions were about 2 times the concrete shear resistance, despite the cement replacement levels being low. In terms of crack propagation, the fine vertical flexural cracks started to propagate at an early stage of loading and appeared around the mid-span of the beams, with the increase in load, flexural shear cracks were also formed in the vertical direction. The crack angle of the inclined shear cracks in the beams without shear reinforcement ranged between 21 to 26 degrees, and it was observed that the crack angle increased with the presence of shear reinforcement between 12 and 22%. So the angle here versus the angles here. To provide further verification on the results of the high volume fly ash SCC shear study, the results of the present study were compared to shear behavior study conducted by Carlos Ortega. And here you can see the comparison to the Ortega study of the conventional concrete as well as the HVEA-SCC. There is no major difference between the shear strength of the high volume fly ash SCC and the conventional concrete regardless of the concrete compressive strength. There is no trends found between the cement replacement level and the PDCR. And the only difference that can be observed is the effective longitudinal reinforcement ratios. Ductility was also a desirable structural property for the concrete member, so this was investigated. As you can see in the figure on the right, the bar graph shows the shear ductility calculated by the relationship of A at ultimate over A at yield, at apparent yield. And you can see that actually the high volume SCC 70 provided greater shear ductility than the conventional concrete with 100% Portland cement. Here you can see the experimental data of the different high volume fly ash values. Other SCC databases without the high volume fly ash in them, as well as the conventional concrete results. You can see that our test results are generally on the lower side of the band of test data, which may warrant the consideration eventually, as more data is obtained, of a correction factor for this type of concrete. But it does exceed the current minimum ACI equation limit. Now on to bond behavior. Due to the poor tensile strength of the concrete, steel reinforcement needs to be used to obtain a complete composite behavior. So the tensile strength will be fully transferred to the steel from the concrete. And as you can see, there's two different ways that steel reinforcement and concrete transfer loads. It's by mechanical end bearing of the lugs on the bar as well as friction. And there are 4 different types of tests that can be used to assess the efficiency and how well the bond of steel is to concrete. In our particular study, we focused on the beam splice test because this test actually puts the bars in flexure and is more representative of an actual reinforced concrete beam bond behavior. Why bond strength? As mentioned, it's very important in terms of the force transfer, and using a high amount of fly ash could affect the chemical adhesion as well as the frictional resistance between the bar and the concrete. So we're very interested to see how well this performs. We also undertook an experimental study on the bond performance, and here you can see the parameters used in terms of the beams, the splice lengths. In some specimens, these splices occurred on the bottom, and on others on the top to see if there was a top bar effect in the splice. And here you can see the test matrix. Due to time considerations, I won't go into the very small details. Here you can see the fabrication of the cages as well as the production of it. Just going to show you in this very brief video here the flowability of the high volume self-consolidating concrete. So you can see no labor is required to vibrate the concrete, and there is no segregation in the mix that we developed, meaning the aggregates are evenly distributed between the bottom and the top of the concrete element. In this test study, we looked at with and without confinement around the lap splice area. Here you can see without confinement. Here you can see with confinement. Here you can see the test setup as well as the displacement rate during the test. Here are the results. The results show us that adding transverse reinforcement in the splice zone changed the mode of failure from splitting to pullout. The top splice beams experienced a 1.7% increase in the peak load compared to that of the bottom splice beam. This observation indicates that the high volume fly ash SCC mixes were very stable due to the very low water cement ratio and the use of a high amount of fly ash, which may have resulted in a decrease in the amount of bleeding water accumulated beneath the top bar. In addition, the 3 days curing may have helped to have a cover strength higher than that with the bottom splice beams. And here you can see the splitting failure along the length of the horizontal splice and the crack patterns experienced by the splice beams without confinement were essentially identical. Confined beams with transverse stirrups in the splice zone had a slightly different crack pattern than beams without confinement. In order to investigate the effect of cement replacement on strain behavior, the recorded data for each group, BWOC, BWC, and TWOC, were plotted in load versus strain format as shown in the figures. According to the plots, each group of specimens displayed almost similar behavior during testing except preflexural cracking stages of 70% cement replacement. The 70% specimens had much greater crack load than the others did. The results of the measured strains indicated that each specimen ultimately failed due to the bond around the splice rebar. When plotted here, you can see the curve fit that was developed for these series of tests, as well as a database that we have at Missouri S&T on conventional concrete. And you can see they all generally follow the same empirical relationship for bond. Conclusions. All high volume fly ash SCC mixes exhibited excellent rheological properties. The compressive strength of the high volume fly ash SCC mixes developed an early age compressive strength greater than our target value of 2,500. All the mixes with air entrainment exhibited excellent performance in terms of freeze-thaw resistance. In terms of shear strength, there was no major difference between the behavior of this new mix, classification, and conventional concrete beams. The top splice beams exhibited a higher peak load than beams cast with bottom splices, and usually it's the opposite. So this showed us our mix was very well distributed. Confinement in the splice zones did not show any significant improvement, and the presence of transverse reinforcement in the splice zone changed the mode of failure and the crack patterns only. Splice beams experimental results showed that the high volume SCC mixes are consistent with conventional concrete, self-consolidating concrete, and high volume fly ash concrete. And most importantly, from the perspective of sustainability and CO2 emissions, each 1 cubic yard of high volume fly ash SCC used in the place of a traditional ordinary Portland cement based concrete would be reducing the embedded CO2 costs by 500 pounds. I guess I want to ask at this point, our moderator, I think I'm really towards the end of my time. Should I continue on with part B or wrap up my lecture at this point? It'll probably take another 10 minutes. I guess I will continue.
Okay,
Yeah.
so yeah, okay, so you can have some 5-10 minutes more, no problem.
Okay. All right, I will continue on. I'm going to move on to part B, and it's worthy to mention that this is part of a teamwork. So there was also several other key team members that helped with part B of this project, including Ellie Hernandez, Alex Griffin, and Kaylee Smith. So now I want to talk about field application of high strength SCC in bridge girders. And here are the overview of part B that I will follow. Infrastructure, of course, is the backbone of our world economy and our nation's economy. For example, Missouri in the US, which is where I'm from, there are more than 800 bridges that have been rated as poor or deficient. The average age of our bridges in Missouri is 46 years, and most of the bridges were designed to last only 50 years. So therefore, 60% of Missouri bridges are beyond their original intended lifetime. So in order to address this, we need to think of more durable, longer lasting, more sustainable ways to develop our new bridge systems. And recent developments in the United States with aging infrastructure has created this desire and need to develop these sustainable concrete mixtures. And one such of those is what's called high strength self-consolidating concrete. This is a new innovative concrete that has all the benefits of SCC, as we've talked about, the flowability, the stability, with the added benefit of strength. So the strength is equal to or greater than 8,000. And this helps to have more compact sections. This helps us in terms of efficiency of production. And this can also improve the microstructure and durability. However, there's concerns when using in pre-stressed concrete. How does it affect the pre-stress losses, the stiffness of the concrete, as well as some of the issues we discussed for high volume fly ash concrete, including bond and shear and the thermal behavior. So to answer these questions, we developed a research program to investigate all of these key issues. Due to time constraints, I will only talk about bridge temperature in the next few minutes. In particular, we wanted to see if this type of concrete affected the thermal behavior of a new bridge that was built recently in Missouri in the US. To investigate the applicability of this concrete, we used well-established empirical models developed by AASHTO LRFD in the United States and NCHRP Report 276. These are both used to predict uniform bridge temperatures of high-strength SCC. The bridge itself is located near our state capital of Jefferson City, Missouri, right outside of the town of Lynn, Missouri. It is a 3-span bridge, and this bridge structure was fully instrumented, including the girders, the bridge panel, as well as the bridge deck, with vibrating wire strain gauges that could measure both the temperature as well as the strains in the bridge. Innovative concrete was also used in this bridge. High-strength self-consolidating concrete was used in girder span 2, while high-strength concrete was used in girder span 1, and normal strength SCC was used in girder span 3. The bents also incorporated high-volume fly ash concrete, the first use of it in the state of Missouri, and one of the few probably in the United States with a 50% fly ash replacement level. Here are the mix designs. I won't go into the details due to time, but the big thing to note in the SCC mix designs is that there is a reduction in the amount of coarse aggregate and an increase in the fines, as well as a reduction in the size of the coarse aggregate, as we have discussed about self-consolidating concrete. The concrete properties you can see here, both in terms of the compressive strength development, well above 8,000, as well as the property of the deck and some of the properties of the fresh concrete. Two of the girders of each span were instrumented. Here you can see the instrumentation of the vibrating wire strain gauges. We've done this in previous studies over the years. And this project also had a data acquisition system, a solar panel to power the data acquisition system, and a cellular feature to transfer data from the bridge site to the university. And here you can see some of the instrumentation prior to fabrication of the pre-stressed precast girders, some of the instrumentation in the deck, the location, as well as the spans that were instrumented. We only instrumented half of the girders because during load testing and other studies, we could reciprocate results by moving the loads around. Uniform bridge temperatures are critical because of seasonal changes, expansion, and contraction due to thermal changes, and this can affect the bridge behavior. If this is not considered in design, especially in continuous constructions, it can result in cracking and deterioration of the bridges and structures. In order to evaluate the behavior of the concrete, we had to understand what the thermal expansion and the coefficient of expansion and contraction is. In order to do that, we could make specimens and put them in a freezer, put them in an oven to then develop the coefficient of thermal expansion of each of these materials that was used in the actual bridge construction. AASHTO LRFD 2018 provides a procedure based on your location in order to help estimate what the uniform bridge temperature of your structure is. And we use that along with the NCHRP report to compare our measured experimental values to the current recommended guidelines. Here you can see the approach based on the instrumented LVD, the instrumented gauges that we had in the structure. We used a weighted average based on the cross-sectional area to then help calculate the annual daily bridge temperatures and the average bridge temperatures. This just shows some of the peaks throughout the year, that occur due to seasonal changes, peaks and minimums measured during the day. And here you can see it broken down into maximum ambient temperature, minimum ambient temperature of the peaks, both top and bottom, high and low, and as well as the maximum and minimum beam temperature relative to girder 3 and girder 4 in the high strength SCC. The maximum ABTs were 90 degrees or 32 degrees C, 92 degrees Fahrenheit or 33 degrees C for girder 3 and girder 4 in span 2 respectively. And the minimum ABTs were 1 degree F or minus 1 degree F and minus 18 degrees Celsius, minus 2 degree F and minus 20 degrees Celsius respectively for those same girders. As you can see at the bottom in equation 1 and equation 2, these are the equations developed and proposed by the researchers to help determine the average daily extreme temperatures. Someone may ask, is it important concern about thermal strain? To answer this question, we did a comparison between the strain induced from the temperature variation and the critical case of live load test, we found that the strain caused by uniform temperature is approximately 2.3 times the strain caused by a H20 dump truck on the bridge. So you can see that the strain caused is significantly different for thermal effects, so they can be quite significant. So 215 due just to temperature changes, and 95 due to 6 H20 dump trucks on the structure. In conclusion, the health monitoring system was successfully installed on bridge A7957, and all of the vibrating wire strain gauges and built-in data acquisition system has worked perfectly for more than 2 years of continuous monitoring. The methods for effective bridge temperature provided by NCHRP report and AASHTO LRFD specifications did not accurately reflect the extreme temperature measured in this study. And in general, the high strength self-consolidating concrete can be considered a sustainable concrete option to construct bridge structures, and design specifications still require some modifications to accommodate the material composition of high strength SCC. And with that, I would like to thank many staff members, technicians at our institution, many graduate students in my research team, as you can see here, that helped with this work, as well as the sponsoring agencies for this research study. And with that, I thank you for your attention. I thank you for your time, and I would be happy to field any questions. Thank you very much.